Everyone. So today we are going to start the sixth part of chapter 9, and in this part we will discuss the one design problem for the shell and tube heat exchanger. So as the name suggests, design problem. So in this problem, usually in these types of problems, usually the heat exchanger size is not given, and they don't tell about the heat exchanger. So basically, you have to select size and type of the heat exchanger. So as we read the problem, that the gasoline, the properties of the gasoline is given here, and it is flowing at a rate of 8.82 kg per second and is to be cooled from 93.3 degrees Celsius to 48.9 degrees Celsius. So this is the requirement, that you have gasoline and which is flowing at a rate of 8.82 kg per second, and it is to be cooled from 93.3 to 48.9 degrees Celsius. And what is available is the city water, and it is available at a temperature of 26.7 degrees Celsius. And then we need to determine the specification of the heat exchanger that will perform this service. Okay, so we are in the shell and tube heat exchanger chapter, so we will select shell and tube heat exchanger. So before we select and before we choose the right size for the shell and tube heat exchanger, then we need to follow certain design constraint and criteria to start the design. Okay. So remember that there are several design criteria. So the one of the criteria for the shell and tube heat exchanger is that the velocity in the tube side should be economic velocity, and the pressure drop either in the tube side or shell side should not exceed by 70 kilopascal, and the correction factor for the shell and tube heat exchanger should be greater than 0.75. So we will see that when we select our heat exchanger, then we should accommodate all these criteria. Okay. So the mass flow rate is given, and the inlet and exit temperature is given for the gasoline, and as for the properties, we use the same technique as we used in double pipe heat exchanger. If both the temperatures are given, we will use the average temperature to find out the properties, and if one temperature is given, then we will take the suitable average temperature. Okay. So here our warm fluid is water, warm fluid is gasoline, which is to be cooled from 93.3 to 48.9, and cold fluid is water. Okay. So we can calculate the rate of heat transfer for the gasoline, since the mass flow rate is given and the specific heat we can get from the properties, and the temperature, the initial temperature and desired temperature is given. So we can calculate the heat transfer, so which comes out to be 8.2 10 raised to the power 5 watt. Okay. So this should be equal to the heat transfer by the cold fluid. As for the cold fluid, we do not have mass flow rate. Properties we can take at suitable temperature, and we do not have the exit temperature, we only have the inlet temperature. So in this case, we have two unknowns, mass flow rate as well as the temperature. Okay. So we will check first of all the correction factor, and for the correction factor F, and for the correction factor we need to know that what is S, and we need to know and what is R. So these two parameters. So by the definition, the R is MC CPC over MW CPW, and which can also be written in terms of temperatures. Okay. So the mass flow rate for the cold fluid we don't have, and if you see from the temperature side, the T2 we don't have. For the S, then the T2 again we don't have. So how can we check the correction factor even before selecting the shell and tube heat exchanger? Because the correction factor will tell us whether the shell and tube heat exchanger will work for this application or not. If the correction factor is greater than 0.75, then only we can be assured that the shell and tube heat exchanger will work, and will work economically basically. So, the shell and tube heat exchanger will work economically if the correction factor is greater than 0.75. Okay. So, here we have the two expression, then this one is for R and this one is for S, and in both cases we do not have the T2 temperature. Okay. So, what we do that we know the initial temperature of the water. So, the initial temperature of water is 26.7 degrees Celsius. So, the final temperature of the water must be greater than this temperature. So, we will start with some suitable exit temperature, and this is our assumed temperature, and we will prepare a table. Okay, let us we assume the T2 and then we substituted the T2 in this value and this value, and then we calculated the R and S, and finally with the help of R and S, when we go to the figure 9.2, then we can find the value for correction factor. So, the correction factor in this case comes out to be 0.98. So, then we take some certain values, maybe like 4 or 5 values, possible values. So, it can be 37, it can be 43, it can be 48, or it can be 30, even less than that, right. So, for certain values of T2, we saw that the correction factor is all for all values it is above 0.75. So, that means wherever the T2 falls, the correction factor value is greater than 0.75. So, this justifies that the shell and tube heat exchanger can be selected for this application. Okay, fine. So, remember that we do not have actual T2 and we do not have the mass flow rate for the cold fluid. So, how can we start with? So, we can start with by choosing, by taking the arbitrary we arbitrarily use an outlet temperature of the water T2 as 35.6 degrees Celsius. So, and this is only for the mass purpose. We need to actually check this temperature at the end. So, only for the mass purpose that we need to find out that what is the mass flow rate, because in this equation if you substitute the T2 here, then you can get that what mass flow rate do you actually need for the cold fluid. So, it depends upon the T2, right. So, we initially we are assuming that our T2 is going to be 35.6 degrees Celsius. So, in the beginning we are assuming that the T2 is 35.6 degree Celsius. So, and the mass flow rate comes out to be 22.05 kg per second. Okay. So, remember that the T2 parameters are depending upon the shell and tube heat exchanger. So, the final temperature T2 for the cold because our objective is to cool the gasoline from 93.3 degrees Celsius to 48.9 degrees Celsius. So, the rate of heat transfer depends upon that how much you cool this. If you are achieving this 48.9 degrees Celsius, then you are getting this value of heat transfer, and based on this value of heat transfer you will get that what is your T2. So, T2 basically depends upon that how much you are getting the exit temperature for the gasoline. Okay. So, to start the solution we are assuming that the small T2 is 35.6 degrees Celsius, and when you substitute in this expression of the mass flow rate, that the mass flow rate equals to the rate of heat transfer Q divided by the Cp and divided by the temperature difference. So, it comes out to be 22.05 kg per second. So, now we have the mass flow rate for the cold fluid also. So, this is just for to design the to get the some workable mass flow rate. Okay. So, this is one way of doing it. Other way of doing it that we can equate the mass velocity of the cold fluid with the warm fluid to get the mass flow rate. But anyway, we are using this method to get to the mass flow rate of the fluid where the mass flow rate is not given. Okay. So, now we begin our solution by selecting the heat exchanger. So, the selection of inner diameter and the fluid routing. So, about the routing of the fluid we discussed before that there are several factors it is viscosity and this pressure and its corrosion tendency and falling factor, several factors. So, based on that we can decide that which fluid should be routed through the tubes. Okay. So, here what they are saying that the gasoline and organic liquid and water both fall the surface at the same rate. So, we arbitrarily route the gasoline through the tubes. So, we are routing the gasoline through the tubes and the water is going through the shells. Okay. So, remember that when the gasoline is routing through the tubes, then we need to know the economic velocity of the gasoline. So, the economic velocity, it is a range. So, out of the range you can choose certain velocity, let us say it is 1.8 meter per second is the economic velocity for the gasoline. Now, we can start our selection. So, first of all, arbitrarily we have to select the shell inner diameter. So, we can start anywhere from the table. So, what we have the shell diameter tables as we saw before, like this is one table, another table, another table. So, here we can take any value out of these shell diameter. So, the several shell diameters are given. So, we can choose any value. Similarly, about the tube distribution, outer diameter of the tube, again you can choose the outer diameter of the tube of your choice, because we do not have any constraint for that. Now, for the pitch, again you have to decide whether you are going to choose the 1 1/4 pitch and you are going to triangular pitch. So, either you can choose from this table or from this table where your tube diameter is 3/4 and the pitch is 1 inch and the distribution is square. So, basically you can take any combination, and you can start with any diameter. You can start with any diameter from top to bottom. So, in our problem what we selected, so here we can see that what we selected. So, we started with 13/4 ID shell diameter. So, this is the shell diameter that we started with. Okay. So, how do we check whether it is correct or not? So, when you finally solve it, and then you will see that whether you are meeting your requirements or not. If it is you are meeting with your requirements, then this size is fine, and if you are exceeding your requirement, then you have to choose the smaller size, and if you are not meeting, still you are short of your requirement, then you can go for larger size. Okay. So, after having this selecting this inner diameter for the shell, then we need to go to the tube combination. So, for the tube size, we decided that we are going 3/4 inch inner diameter tube. Again, that it is up to you, you can choose 3/4 inch and you can choose 1 inch tube inner diameter as long as it is not breaking any constraint. So, and we choose the 13 BWG. So, here again there is you can choose any BWG depending upon your requirement, depending upon what strength of the tube you want. It can be 13, 14, 15, 16, 17, 18, and the pitch, it can be 1 inch or it can be 3/4 inch. So, 1 inch, and the tube distribution is square. Okay. So, it is 3/4 inch tube inner diameter, 13 BWG, the pitch is 1 inch and is square distribution. Okay. Then we go to the table, that which table basically we choose this from. So, 3/4 inch, 1 inch pitch, square distribution. So, it seems that we choose from this table, and what we choose 13 and half. So, if you choose a 13 and quarter, if you choose the 1 pass, then the number of tubes are 97, and if you choose the 2 pass, then number of tubes are 90, and if you choose the 4 pass, then the number of tubes are 82. Okay. So, with this choice, when we go back to our problem, so first of all you start with, it's up to you, you can start with the 1 pass, you can start with the 2 pass, and you can start with the 4 passes. So, in this solution in the book they started with the 4 passes, and they selected the 82 tubes, but they saw that when they complete the calculation their pressure drop was exceeding the 70 kilopascal, which is a constraint for the pressure drop. So, your constraint is violated. So, the 4 passes were not following your constraint. Then you reduce them to 2 passes. When you made the 2 passes, then the number of tubes becomes 90, right, and the pressure drop becomes 20. So, we will go with this solution, that the 2 passes and number of tubes are 90. Okay. So, now the tube size is, everything is clear, that the 13 by 4 inch inner diameter of the tube, 13 BWG. So, this is the tube diameter and 13 BWG. Then we can find the inner diameter of the tube also, and this is 1 inch square pitch. So, remember that this is 3 by 4 inch is the diameter of the tube, and I am sorry to say that this is not inner diameter, this is the outer diameter. Inner diameter you will get out from the BWG table. So, for 3 by 4 inch what is the inner diameter for the tube? Then we will go for BWG table. So, here, so we go for BWG table. For the BWG table, for the 13 BWG, the inner diameter is 14.2 millimeter. Okay. So, the inner diameter is 14.2 millimeter. And so what is the next step? The next step, that you have all the dimensions for the shell and you have all the dimensions for the tube side, and we have the length, available length. The length available for the heat exchangers are 2.44, 3.66 and 4.88 meter. And then how many baffles we can place in the shell? So, we have the criteria for the baffles also, we discussed before that. The maximum spacing for the baffles can be equal to the shell diameter, and the minimum can be 1/5 of the shell diameter. So, you can choose the baffle spacing anywhere between the two limits, and the baffle numbers should come out to be in integer. So, the length in the beginning they choose the 2.44 meter, and in this they placed 7 baffles, and with the 7 baffles the spacing comes out to be 3.5 millimeter. So, this spacing is well within the 336.6 millimeter, because this is your shell diameter. So, the baffle spacing is less than that, and so this is within the constraint. Your constraint is that the baffle spacing should be maximum, it should be equal to the shell diameter, and minimum it should be 1/5 of the shell diameter. Okay. So, now you have almost all parameters known for your heat exchanger. You have length, you have shell diameter, you have baffle spacing, you have number of baffles, you have number of passes, you have number of tubes, tube inner diameter, tube outer diameter, and so on. Okay. Now, you have to apply the heat exchanger calculation procedure step by step to your problem. Okay. So, now look at this table. So, we selected this as our shell diameter, and we choose the number of tubes 90 and the number of passes 2, and the length we selected this, and the number of baffle is this. Then what is next step? The next step is to calculate the flow area for the tube side, to calculate the flow velocity for the tube side, to calculate the Reynolds number for the tube side, to calculate the Nusselt number for the tube side, and to calculate the heat transfer coefficient. So, because the geometrical parameters we all have, and we have the all flow rate. So, once we have all these things, then the design problem becomes the analysis problem. Basically, you have the mass flow rate and you have the heat exchanger size. So, if we go back to our analysis problem that we did, so So basically from here we have to start. You need to start to calculating the flow rate, and then you need to start calculating the velocities, and then the shell diameter, and then the Reynolds number, and then the Nusselt number, and then the convection coefficients, and then overall heat transfer coefficients, and then R, C and N parameters, and then effectiveness, and then finally you need to calculate the temperatures. Okay. So when you calculate these two temperatures, then you are basically reach at this point in the table here, this point in the table here. So your temperature T2 comes out to be 60.55 degree Celsius. So what is your requirement? You need to cool the gasoline from 93.3 degrees Celsius to 48.9 degrees Celsius. So your requirements are not meeting yet. So what you will do next? And one more thing that we need to check here is that what is our pressure drop. So the pressure drop here is 20 kilopascal for the tube side and 11 kilopascal for the shell side. So the pressure drops are well within the limits. The limit is 70 kilopascal, but your temperature is not meeting. So what you can do from here? So we have several options. The one option is that we can increase the number of passes, but the number of passes will give you the higher pressure, and it has been checked before. So other thing is that you can increase the length. So in the second option, they are keeping the shell diameter same, and the number of tubes are same, number of passes are same. They are increasing the length of the heat exchanger. So the length is increased to 3.66 meter, and when the length is increased, then the number of baffles will also be increased. So you have to recalculate the number of baffles, how many baffles you can accommodate now. Okay, and then you calculated your T2 again. So T2 comes out to be 52.22, so which is again not meeting our requirement. So this is not this will also not be accepted. Okay, then what next? What we can do next? So we can further increase the length, because we have the three length options: 2.44, 3.66 and 4.88. Now we are choosing the 4.88 length, and the number of baffles are changed accordingly, and this time we are getting the temperature 46.11. So which is meeting our requirement? Our requirement was to cool from 93 to 48, but this is cooling a little more, 46.11. Okay, so this is our acceptable solution. But remember here that we have not included the falling factor in our calculation. So this solution will work when the heat exchanger is new. So the R2 is indicating that this solution will work when the heat exchanger is new, and when the heat exchanger is old and there a falling takes place, then we may not get this temperature. Okay, so what we can do, we can further try with higher diameter shell. So this time we increase the shell diameter, and accordingly we got the higher number of tubes and the two passes again, and we started with the smaller length 2.44, and number of baffles are 6, and this time we got the temperature 58.89 degree Celsius, so which is not meeting our requirement. Then we go for higher length 3.6, then it come out to be 50, then again this is not meeting our requirement. Then we go for further higher length, and then this time we are getting it 44. So this time we are meeting our requirement. So if you are satisfied with this, you can stop your solution here, that you met your requirement. And if you further want to go if you further want to drop the temperature, then you can go for further higher diameter, and you can try it, and then finally you are getting that your T2 comes out to be 41.11 degrees Celsius, which is much less than what you need. So this is definitely will work even after the falling. So this is what they suggesting, that you are well below the required temperature. Your required temperature is 48.9, but you are getting well below it. So even if the heat exchanger is falling, even after 1 year or 2 year usage, you can still get 48.9 degrees Celsius. So this is how we complete the design problem. So the design problem in summary in the beginning, basically you have to select the certain parameter: shell diameter, tube distribution, tube pitch, and BWG selection, etc., etc. And once you have all the parameters of the heat exchanger, then you have to analyze in the same way as it is a analysis problem, and then you have to check whether you are meeting your requirements or not. So this is how we do this design problem. Hope you got the idea about this, and then on the finally we can summarize the information of our design. So this is the summary of information, that the shell size and fluid passes, and the tube passes, the shell passes. This is always one shell in our problems, and this is 4 passes, and the number of tubes, and the number of baffles, and the tube specification, and the mass flow rate for the cold fluid, and the temperature. So the T2 comes out to be 36.11, and this T2 comes out to be 46.66, and the pressure drop is well within the 70 kilopascal. Okay, so here we complete this solution. Hope you understand this, and probably in the online sessions we will do one problem, so that you can have some if you have any problem or any confusion, then we will talk about that. Okay, so thank you so much for your attention.